Refrigerant 22, 4-cylinder, automated compressor at 29 revolution per second. Condensing temperature is 40 C. Evaporating temperature is negative 40 C. 4 C. Refrigeration capacity is 115 kilowatt. This is Q. Motor efficiency is 90% H of M. So motor is 34.5 kilowatt P of M. Bore is 87 mm or 0.087 meters diameter. D. Piston stroke is 70 mm, 0.070 m or L. 8 degrees C of cooling. Wait, required A is actual volumetric efficiency, B decompression efficiency. Solution, so this is the graph. Then sabi dito, condensing negative 4, negative 4, ito yung condenser na 40C. 40C, kunin mo saturation pressure, ito yung pressure na yan. 1 to 2, isentropic, then 3 to 4. Meron tayong subcooling. Binanggit yan, subcooling na. So, yan. Yung 3 on all bante sa saturation curve. 3, then 4 to 1. Okay? So, yan ang tamang phase charge. Okay? Pag itang problem, pero ikaw, wag nandito lang. So, mali na. Okay? Dapat tama lang yung drawing niya. So, reference, yung Stoker and Jones, properties, table A-6, negative 4C, evaporated temperature, yung saturation niya is, H of 1 is 403.876 kJ per kilogram. Suction is 53.5682 liters per kilogram. The entropy is 1.75775 kJ per kilogram Kelvin. Sa at 2, so gamit kayo ng diagram niya o yung figure. Ay, hindi, table pala. So, table A7 kasi R2 o R2 to further than 22. Constant entropy, 40C temperature. So, mag-interpolate kayo. H2 is equal to 435.391 kJ per kilogram. Discharge is 17.314 liter per kilogram. Yung piece of 2. At 3, so 40C condensing temperature. So, table A is 8C subcooling. So, temperature is 40 minus 8 is equal to 32C. Then, kunin nyo yung H of F doon, yun yung H of 3 at 32C. So, 239.23 kJ per kilogram. Then, H of 4 is equal to H of 3, also 239.23 kJ per kilogram. Kasi, so, may properties ka na yan. 1, 2, 3, 4. So, for actual volumetric efficiency, kunin mo yung displacement. Displacement rate is 4-cylinder times 29 revolution per second times yung volume ng cylinder is 5/4 D squared times L. Yan ang volume ng cylinder. Since apat yun, kaya na-multiply ito. Okay? Per cylinder, per revolution. So, magiging ano to. Substitute mo yung value 0.087. So, 4-cylinder times 29 revolution per second times 5/4 times 0.087 squared times 0.07 is 0.04827 cubic meter per kilogram. Or 48.27 liter per kilogram. Bakit nga pala per kilogram? So wait, hindi ito per kilogram. So this is per second. Okay? Per second. Okay? Wait lang. So next, the actual rate of refrigerant flow is Q over H of 1 minus H of 4 or 115 times kilowatt divided by 403.876 minus 239.23. So, magiging 0.6985 kilogram per second. So, yung units, yan, this is kilojoule per second. Di ba? So, matitira, kilogram per second. So, actual volumetric flow rate at compressor suction now is W times the suction specific speed, which is 0.6985 kilogram per second times 53.5682 liters per kilogram is 37.42 liters per second. Now, the actual volumetric efficiency is the volume flow rate in direct compression divided by displacement rate of compressor, or 37.42 over 48.27 times 100 is 77.5%. This is the answer. Ang efficiency is always in percentage. Hindi sa sinabing ratio. Ang ratio, 100% yun. Next, always use percentage as possible. So, B, compression efficiency. So, the actual work is the actual work of compression is equal to, so ayusin muna natin to. So, the actual work of compression is 0.9 times 34.5 kilowatt divided by 0.6985 kilogram per second is 44.45 kilojoule per kilogram. So, yung efficiency kasi, this is a work done. So, the actual work is the power of motor. Diba? Motor to. Yan. So, motor mo, 34.5. Multiply mo ng 0.9. Ito yung sa compressor. So, kaya, ito na. So, this is the actual work of compression. Then, M sub C is equal to compression efficiency, isentropic work of compression divided by the actual work of compression, which is H sub 2 minus H sub 1 over the actual work of compression, or 435.391 minus 403.876 divided by 44.45 times 100 is 70.9%. So, ito na yung answer mo, 70.9%. Next, compression discharge temperature. If the discharge temperature of the refrigerant from the compressor becomes too high, it may result in the breakdown of the oil, causing excessive wear or reduced life of the valve, particularly the discharge valves. In general, the higher the pressure ratio, the higher the discharge temperature. But the properties of refrigerant are also crucial. So figure 17 shows the discharge temperatures for four refrigerant following isentropic compression from saturated vapor at 0 to various condensing temperature. So this is figure 17. Example, dito yung condensing temperature mo. Ito yung discharge temperature ng mga ammonia. Ammonia, refrigerant 22, 27, pinakamataas yung ammonia. Okay? Refrigerant 12 and 502 have low discharge temperature, while refrigerant 22 experiences higher temperature. Since the highest temperature of the fourth refrigerant zone is ammonia, ammonia compressors are equipped with water-cooled heads. Next type is the rotary screw compressor. Ito yung itsura niya, rotating screw. Rotary screw compressor are also positive displacement compressor. Two meshing screw rotors rotate in opposite direction, trapping refrigerant vapor and reducing the volume of the refrigerant along the rotor to the discharge point. Ito yung mga parts. Okay? Refrigerant inlet ito. So compression and out. Next type is the centrifugal compressor. Centrifugal compressors are dynamic compressors. This compressor raises the pressure of the refrigerant by imparting velocity or dynamic energy. Yan. Using a rotating impeller, ito. Yan. And converting it to pressure energy. Now, to compute the tip speed to develop pressure, a rough estimate of the tip speed of the impeller can be made by using several fundamental relationships for turbo machinery o yung fluid machinery. The torque the impeller easily impart to the gas is T is equal to W times P sub 2 T R sub 2 minus P sub 1 T R sub 1, where T is the torque, W is the mass rate of flow per meter per second, P sub 2 T, oops, so yan. V sub 2T is the tangential velocity of refrigerant leaving the impeller, meter per second. R sub 2 is the radius of exit of the impeller. V sub 1T is the tangential velocity of refrigerant entering impeller, meter per second. R sub 1 is the radius of inlet of impeller, meter. So, fluid machinery subject nyo, medyo alam ko, gamit na gamit yung mga symbols doon. Okay? If the refrigerant enters impeller in an essentially radial direction, I need to repeat, the tangential component of the velocity v sub 1 t is equal to 0. So t is equal to w v sub 2 t r2. Now, the power required at the shaft is the product of the torque and the rotative speed. P is equal to T times omega, angular speed, times or W times V sub 2T R sub 2 times omega. Replace the power in watts or kilowatts. And omega or W is the rotative speed in meter per second. So at very low refrigerant flow rate, the rotative speed of the impeller and the tangential velocity of the refrigerant are nearly identical. Therefore, R sub 2 W is equal to V sub 2 T and P is equal to W times V sub 2 T squared. Yeah. Equation 15. Another expression for ideal power is the product of mass, rate of flow, and the isentropic work of compression. So ito, W times delta S times 1,000 kilojoule per kilogram. Oh, wait. Times 1,000. This is a conversion to. Wait. So this is 1,000. The power mo, sabi dito in watts, kasi ito meter kilogram per second, this is magiging meter per second squared. So, meter squared per second squared, tapos ito kilogram per second. So, magiging watts. Okay? So, ang power mo is in watts. So, ito naman, kaya may 1,000 dito, ito, okay lang to. Watts dito. Kilogram per second, meter squared per second squared, and this is watts. So, ito, kailangan mo may 1,000 na factor to convert the kilojoule per kilogram na value nito to 1,000 to joule per second per kilogram. So, magiging kilogram per second naman to. So, magiging watts in joules. Okay. So, yung watts, 2 watts. So, equating the expression for power, magiging V sub 2T squared is equal to 1,000 times delta SI. Delta SI is in kilojoule per kilogram. This is for SI units. Okay? Pag binigyan kayo ng English units, alam niyo na yung equivalent to 778.16. Kasi ito, BTU per pound. So, bala lang kayo sa units. Convert nyo, magamit dito yung 778.16 foot-pounds per BTU. Yan ang conversion sa delta S. So, consistent na lang. Although equation 17 is based on some idealization, it can provide an order of magnitude estimate of the tip speed and can also draw sa show important comparison. Sa mga blower sa pump, mayroon sila niya tawag tip speed, yung pinaka-paglabas na mismo ng outlet. So, yan. So, example 5, a two-stage centrifugal compressor operating at 60 revolutions per second is to compress refrigerant 11 from an evaporating temperature of 4C to a condensing temperature of 45C. If both wheels are to be of the same diameter, what is the diameter? Given two-stage 60 revolutions per second, refrigerant 11, evaporating temperature 4C, condensing temperature 35C, required diameter 12. Solution at 4C, evaporating temperature table 8 as 4, Stoker and Jones, X sub 1 is 1390.93 kilojoule per kilogram. S sub 1 is equal to 1.68888 kilojoule per kilogram per Kelvin. Then at 35C, condensing temperature, figure A2, constant entropy, H sub 2 is equal to 410 kilojoule per kilogram. W is 60 revolution per second or 125 radians per second. So equation 11 and 16, P sub 2T squared is equal to 1000 times delta H, I. Then P sub 2T squared is equal to 1000 times H2 minus H1 over 2. Bakit? 2 stage to eh. Kaya natin yung diameter ng dalawang wheel mo per stage. So, atiin mo yung delta S mo. O S2 minus H1 mo sa 2. So, P sub 2T squared is 1000 times 410 minus 390.93 divided by 2 is 97.65 meter per second per stage. So, R sub 2 times W is equal to P sub 2T. So, T2 over 2 times 125 is 97.65. The diameter is T2 is equal to 0.518 meter. Or pwede mo gawing 518 mm. Next type is the scroll compressor. Scroll. The scroll of paper. Diba? Nakapagin nyo na. Bakit scroll? Ito. So, maliliit na compressor yan. The scroll compressor are also positive displacement compressor. The refrigerant is compressed when one of the spiral orbit around a second stationary spiral, creating smaller and smaller packet and higher pressure. By the time the refrigerant is discharged, it is fully pressurized. So, ito yung mga parts. Kung interesado, tingnan nyo ng mga parts niyan. Wala naman tayo sa maintenance. So, ito. Next are the condensers and evaporators. Dalawang heat exchanger to. So, the most widely used type of condenser and evaporator are seal and tube heat exchanger and the pin coil heat exchanger. Ito yung mga condenser itong dalawa. Yung evaporator. Little evaporator. Evaporator, yun nakita sa mga aircon. So, coil na may pins. Yan. Itong type na to, evaporator sa chiller, ito yan. Yung pin naman, ito sa aircon protector. Pero meron din yung indoor type. Ito yung shielded tube, sikat na sa transfer. Sa anong parameters? Overall heat transfer coefficient. So the overall heat transfer coefficient for an evaporator or condenser is the proportionality constant, which when multiplied by the heat transfer area and the main temperature difference between the fluid yields the rate of heat transfer. Figure 20. If it flows across a tube, as in figure 20, between the refrigerant on outside and water on the inside, for example, under steady state conditions, the rate of heat transfer Q in watts is the same from the refrigerant to the outside surface of the tube, from the outside to inside surface of the tube, and from the inside surface of the tube to the water. Heat transfer niya. Therefore, the expression for Q and each of the heat transfer are Q is H sub O A sub O times T sub O minus T sub O S, surface yan. Q is equal to K over X plus E sub M plus T sub OS minus T sub IS. Q is equal to H sub I, A sub I plus T sub IS minus T sub I. Where Q is the rate of heat transfer in watts, H sub O is the heat transfer coefficient on outside of tube, watts per meter square Kelvin. A sub O is equal to outside area of tube per meter. T sub O, refrigerant temperature. C, tandaan nyo, SI ito. Pag English units, dapat alam nyo na. Diba? T sub O is equal to temperature of outside surface of the tube, VC. K is thermal conductivity of tube metal, watts per meter Kelvin. X, thickness of the tube in meter. T sub IS, temperature of inside surface of tube, VC. E sub M is the main circumferential area of the tube. So, area mo muna, tapos mo average. H sub I is the heat transfer coefficient on inside of tube, 1 per meter square Kelvin. E sub I, inside area of the tube, meter square. T sub I is equal to water temperature and degrees. So, to express the overall heat transfer coefficient, the area on which the coefficient is based must be specified. Two acceptable expressions for the overall heat transfer coefficient are Q is equal to U sub O, A sub O times T sub O minus T sub I, or Q is equal to U sub I, A sub I times T sub O minus T sub I. Well, U sub O is the overall heat transfer coefficient based on outside area. U sub I is the overall heat transfer coefficient based on inside area, watts per meter square Kelvin. From equations 21 and 22, it is clear that U sub O, A sub O is equal to U sub I, A sub I. The U value is always associated with an area. Knowledge of U sub O or U sub I facilitates computation of the rate of heat transfer Q. To compute the U value from the knowledge of individual heat transfer coefficient, first divide equation 18 dito, yan, by H sub O, A sub O, equation 19 by K, A sub M X, and equation 20 by H sub I, A sub I, leaving only the temperature differences on the right side of the equation. Next, add the equation giving Q over H sub O, A sub O, plus Qx over K, A sub M, plus Q over H sub I, A sub I is equal to T sub O minus T sub OS, plus T sub OS minus T sub IS, plus T sub IS minus T, or equal to T sub O minus T sub I. So, alternate expression for T sub O minus T sub I are available from equation 21 and 22. So, T sub O minus T sub I is equal to Q over H U sub O, A sub O, is equal to Q over H U sub I, A sub I. So, equating equation 23 and 24, cancelling Q provides an expression for computing the U value. 1 over U sub O, A sub O is equal to 1 over U sub I, A sub I is equal to 1 over H sub O, A sub O, plus X over K over A sub M plus 1 over S sub I, A sub I. Okay, tingnan nyo yung equation. Hindi yung sinasabi kasi mayroon pa sa inyo. So, ito yung overall heat transfer coefficient mo. Normally, based tayo sa outside area. Depende lang pag specify na yung U value mo is based on inside area. So, for the cases, yung liquid in tube, ito yung heat transfer niya and pressure drop. Kasi kailangan nyo makuha yung pressure drop din. Bukod sa capacity, yung heat transfer, kailangan nyo rin yung pressure drop. Kasi kailangan nyo yan sa system. The expression for the heat transfer coefficient for fluid flowing inside tube is of the form N sub U, NU or Nusselt number is equal to C times R sub E exponent N, P sub R exponent M. Yung R sub E is the Reynolds number, and P sub R is the Prandtl number. P-R-A-N-D-T-L. Spelling niya. Where N and M are exponent. The constant C and exponent in the equation are HT over K is equal to 0.023 times BD rho over mu 0.8 times CP mu over K is 0.4, where H is the convection coefficient, watts per meter squared Kelvin, the ID of the tube, meter, K Thermal conductivity of the fluid, watts per meter Kelvin. B is the mean velocity of fluid, meter per second. Rho is density of fluid, kilogram per cubic meter. Mu is the viscosity of Pascal of fluid in Pascal second. So, convert nyo yung conversion niya sa English SI. Cp is the specific heat of fluid, joule per kilogram Kelvin. Heat joule. Si watts yung gamit natin. Equation 26 is applicable to turbulent flow. Note which typically prevails with the velocities and properties experienced in most commercial evaporators and condensers. Kaya need to consider doon sa lamina. Kasi ito nga, mostly is turbulent na. So example number 6. A refrigerant 22 condenser has 4 water passes and a total of 60 copper tubes that are 14 mm ID and have 2 mm wall thickness. The conductivity of copper is 390 watt per meter Kelvin. The outside of the tube is spinned so that the ratio of the outside to inside area is 1.7. The cooling water flow through the condenser tube is 3.8 liters per second. A. Calculate the water side coefficient if the water is at an average temperature of 30 C, at which temperature K is 0.614 watts per meter Kelvin, Rho is 996 kilogram per cubic meter, and mu is 0.00803 Pascal second. So dito, given yung properties. Kung wala yung binigay na properties, so natin yung sa mga table. So, letter B, using a mean condensing coefficient of 1420 watts per meter squared K, calculate the overall heat transfer coefficient based on the condensing area. So, yeah. So, given require refrigerant 22 condenser, 4 passes, total of 60 copper tubes, 14 mm ID, 2 mm wall thickness, conductivity of copper is 390 watts per meter Kelvin. So, given to, problem din. Pero pag wala, so, kinig sa table ulit. Kay transfer, di ba, tumitingin yung table to. The ratio of outside to inside area is 1.7. Cooling water through condenser tube is 3.8 liters per second. Water at 30 C. So, 4 passes makes a sealing tube to. So, may mga sealing tube kasing may pins din. Ang tawag doon, enhanced surface. Okay. So, water at 30 C. So, ito yung properties. Mean condensing coefficient is 1420 watts per meter squared. Nung refrigerant 22. Refrigerant 22 is outside. So, inside yung water. Okay. Flows through condenser tubes. So, itong given na to is a condenser. Required, yun nga, A, water side coefficient, H2I. B, overall heat transfer coefficient based on condensing area. U sub O. Condensing area mo is yung refrigerant. Diba? Okay. Solution, A, water side coefficient. The equation is SD over K is equal to 0.02 T times BD rho over mu exponent 0.8 times Cp mu over K is 0.4. This equation is for liquid in tubes. So D is 14 mm, 0.014 meter. K is 0.614 watts per meter Kelvin. Then rho is 996 kilogram per cubic meter. Mu is 0.000803 Pascal second. Cp is 4190 joule per kilogram Kelvin. So velocity is Q over A is equal to 3.8 times 10 exponent negative 3 cubic meter per second. Yung flow rate, saan siya mag-flow rate? 4 pass. So ibig sabihin, 60 tube total, latin mo sa 4. So dito papasok yung yung water. 15 tubes per pass. Alam nyo na yung pass, di ba? Per pass sa shell and tube. Then, pi over 4, yung tube area, pi over 4 times 0.014 meter squared. So, the velocity is 1.6457 meters per second. Substitute values dun dito. Yan. So, magiging h times 0.014 over 0.614 is equal to 0.023 times, so basahin ko lang numero, 1.6457 times 0.0145996 over 0.000803 is 0.8 times, numero ulit, 4190 times 0.00803 divided by 0.614, 0.4. So, S of I is equal to 7013 watts per meter squared Kelvin. Answer niya. Letter B, overall heat transfer coefficient. 1 over U sub O A sub O is equal to 1 over H sub O A sub O plus K over X over K A sub M plus 1 over H I A sub I in terms of 1 over U sub O. Ito, 1 over U sub O is equal to 1 over H sub O plus X times E sub M over K A sub M plus E sub M over H sub I A sub I. So H sub O is equal to 1.4 to 1420 watts per meter squared Kelvin. K is equal to 390 watts per meter squared meter Kelvin. A sub O over A sub Y is 1.7. So A sub O over A sub M is equal to 1.25926. Wait, insert natin. So ito, A sub M is equal to 1 half of A sub O plus A sub Y is 1 half of A sub O plus A sub O over 1.7. Then A sub O over A sub M is 1.25926. X is 2 mm or 0.002 meters. S of I is equal to 71 watts per meter squared Kelvin. Substitute values, magiging 1 over U sub O is equal to 1 over 1420 plus 0.002 times 1.2596 over 390 plus 1.7 over 7013. So U sub O is equal to 1060 watts per meter squared Kelvin. This is now the answer. Okay, liquid in tubes. So overall yun. So as the fluid flows inside the tubes to a condenser or evaporator, a pressure drop occurs both in the split tube and in the U-bends, sama yun, or heads of the heat exchanger. Some drop in pressure is also attributable to entrance and exit losses. The expression for pressure drop of fluid flowing in split tube is delta P is FL over D V squared over 2 times rho. So delta P is the pressure drop in Pascal. F is the friction factor dimensionless. L is the length of tube in meter. Now, since the pressure drop in the split tube in an evaporator or condenser may represent only 50 to 80% of the total pressure drop, experimental or catalog data on pressure drop as a function of flow rate are desirable. Okay, kasi merong allowance ganyan, yung mga sa U-bends kasama doon. Ito sa split tube lang. That represents only 50 to 80%. Sa heat transfer, discuss naman yun. Kung nakaabot kayo doon sa shielded tube, yung mga noses doon, sa bending. So, if the pressure drop at one flow is known, it is possible to predict the pressure drop at other flow rates. So the expression available for split tube, equation 27, indicates that the pressure drop is proportional to the square of the velocity and thus the square of flow rate. So the other contributors to pressure drop resulting from changes in flow area and direction are also almost exactly proportional to the square of the flow rate. So if the pressure drop and flow rate delta P1 and W1 are known as flow rate, the pressure drop delta P2 at different flow rate W2 can be predicted like this one. Delta P2 is equal to delta P1 times W2 over W1 squared. Okay? This is the equation 28. So yun, pressure drop. Next, liquid in shell. Shell naman, yung sa labas nito, itong shell. Huwag tayo sa tube. And sealing tube evaporator, where refrigerant boils inside the tube, the liquid evaporator to iba sa condenser kasi condenser condensing. So, the liquid being cooled flows in the shell across bundles of tube as shown schematically in figure 21. Ito yung refrigerant po dito. So, the liquid being chilled. Ayan. So, ito naman is cool down mo. So, ito, evaporating to. Refrigerant. The liquid is directed by bubbles so that it flows across the tube bundle many times and does not short circuit from inlet to the outlet. So note sa condenser, palabas sa loob ng tube. Sa ano naman, sa evaporator, sa loob, palabas sa shell yung liquid. The analytical prediction of the heat transfer coefficient of liquid flowing normal through a tube is a complicated in itself. And the complete flow pattern over a bundle of tube makes the prediction even more difficult. So in order to proceed with the business of designing heat exchanger, engineer resort to correlations that relate tubes and bubbles. Such an equation by Emerson can be modified to the form ST over K is equal to terms controlled by geometry times R sub B exponent 0.6 times PR 0.3 mu over mu sub W is 0.14, where mu is the viscosity of fluid at bulk temperature Pascal per second and average. Mu sub W is the viscosity of fluid at tube wall temperature Pascal second. Kasi magkaibang temperature sa center saka sa wall. So mag-assume ka doon. The Reynolds number in this equation is GD over mu, where G is the mass velocity or mass rate of flow divided by the characteristic flow area, hindi yung actual area. Kasi wala ka makuha actual area yan. Iba-iba. So, meron tayong characteristic flow area. So, one important realization emerges from equation 29. For a given evaporator or condenser, when water flows in the shell outside the tube, the water side heat transfer coefficient is a constant times the flow rate exponent 0.6. The convection coefficient varies as the 0.6 power of the flow rate compared with 0.8 power for flow inside tube. So the pressure drop of liquid flowing through the shell across tube bundle is also difficult to predict analytically. But when an experimental point is available for one flow rate, prediction of pressure drop at other flow rates can be made accurately. Figure 22 shows the water pressure drop taken from catalog data of water chilling evaporator. So the application exponent and the pressure drop flow rate relationship here is 1.9. The water flow rate and pressure drop. This is pressure drop of water flowing in the shell of an evaporator by York division of warm water. So sa catalog to. So pag hindi mo nakuha yung sa circulation empirical, punta ka sa mga catalog, nakuha mo yung pressure drop doon. Depende kasi sa design niya ng manufacturer. So example number 7. A shell tube condenser has U value of a shell tube condenser has a U value of 800 watts per meter squared Kelvin based on the water side area and a water drop of 50 kilopascal rate. So under this operating condition, 40% of the heat transfer resistance is on the water side. If the water flow is doubled, what will be the new U value and the new pressure drop be? The given U sub 1 is 800 watts per meter squared. Kelvin na tatasog strip ka. And delta P1 is 50 kilopascal. 40% of heat transfer resistance is on the water side. Water flow rate double. required new U value or U sub 2. Solution when time U sub 1 as 800 watts per meter square Kelvin. H sub 1 is water side coefficient. So 1 over SI is 40% of the heat transfer resistance. Okay? Resistance, the reciprocal of transfer coefficient. Coefficient. Okay? That's 1 over U sub O. So H sub I is equal to 1 over zero point 0.4 over 1 over 800 is 2,000. For evaporator, water side transfer coefficient is constant times the flow rate 0.6. Replace zero point 0.6 by 0.8 for condenser. So the water side heat transfer coefficient is constant times the flow rate 1.8. And for W2 over W1 is equal to 2. So we have H sub 2 over H sub 1 is equal to W2 over W1 is 0.8. So H sub 2 is equal to 2000 times 2 is 0.8 is 3482.2 watt per meter square Kelvin. Ayan lang. This is not the answer. So, di ba pala, may pressure drop. And the new pressure drop. So wait, walang yung requirement. Now, remaining resistance is 0.6 times 1 over 800 is 0.00075. Kasi yung 40% mo, dito. So, the new U value is 1 over U sub 2 is equal to 1 over S2 plus 0.0075 is equal to 1 over 3482.2 plus 0.00075. So, U sub 2 is 964 watt per meter square Kelvin. So, ito na yung sagot mo pala. Dito. Kasi ito yung H2. Yung bagong H2. Tapos, kunin mo na yung S2 niya, and dagdag mo ito sa tira. Hindi naman nagbago yung resistance ng isa. Okay? So, new pressure drop, delta P2 is equal to delta P1 times W2 over W squared. So, yun lang. W2 over W1 is 2. So, delta P2 is equal to 50 times 2 squared is 200 kilopascal. So, hindi na ako connected dito sa resistance. Next, extended surface pins. Extended surface or pins, ang tawag. Based tayo sa bar pins. The bar pins shown in figure 23 is fundamentally twin whose performance can be predicted analytically and will be used to illustrate some important characteristics. See the figure. The pins are of length L and thickness 2y. The conductivity of the metal is K in watt per meter Kelvin, and the air side coefficient is H of F or watts per meter square Kelvin. To solve for the temperature distribution through the pin, a heat balance can be written about an element of thickness is X in meter. The heat balance states that the rate of heat flow entering the element 1 from the end of the pin plus that heat transfer to the element from the air equals the rate of heat transfer out of the element at position 2 toward the base. Heat transfer nyo to, heat transfer. For 1/2 of pin width and a pin depth of C, the heat balance in symbols is KYZ times derivative of T with respect to X in 1 sub 1 plus CDX of C times derivative of X times H sub F times TA minus T is equal to KYZ times derivative of T with respect to X sub 2, where T sub A is equal to temperature of air, T temperature of pin. And cancelling Z and factoring gives KY times derivative of T with respect to X sub 2 minus derivative of T with respect to X sub 1 is equal to derivative of x times h sub f plus t sub m minus t sub f. For the differential length dx, the change in temperature gradient is, ito na, derivative of t with respect to x sub 2 minus derivative of t with respect to x sub 1 is the derivative of dT over dx with respect to x times dx is equal to second derivative of t with respect to x times dx. Ito, sinimplify lang to. So, magiging, ito na siya. Second derivative of t with respect to x equal to h of f and p sub m minus t over ky. Now, by solving the second order differential equation, equation 34, the temperature distribution throughout the pin can be shown to be t minus tb over t sub m minus t sub b is equal to cosine hyperbolic cosine of m times L minus x. Buo yan, buo. Ito, saka mo sa hyperbolic cosine, divide by hyperbolic cosine of ml. Where T sub B is the temperature of the base of the pin, C, and M is equal to the square root of H sub F over Ky. Derivation of this, look for heat transfer. Book. Okay? So, when a pin coil cools air, point, so this is now the equation of M mo. So, derive. So, ito na yung temperature function. Okay? So, when a pin coil cools air, points in the pin farther away from the base are higher in temperature than point close to the base. Cools the air, diba? Kasi mainit yung air mo, yung sa loob ng, ano mo, ng coil mo, malamig. The net result of the higher temperature of most of the pin is that less heat is transferred than if the entire pin were at temperature T sub B. The ratio of the actual rate of heat transfer to that which would be transferred if the pin were at temperature T sub B is called the pin effectiveness, which is equal to N is actual Q over Q if the pin were at base temperature. So Sharper and Brown found that the pin effectiveness for the bar at figure 2 can be represented by N is equal to hyperbolic tangent of ML divided by the bar pin is not a common shape, but the dominant type of pin surface is the rectangular plate mounted on cylindrical tubes. The net result is a rectangular or a square pin mounted on a circular base, one section of which is section figure 24A. So ayan yung figure 24, merong rectangular plate and B annular pin of the same area. So determining the pin effectiveness of a rectangular plate pin A by treating it as in B, another pin of the same area. So check natin dito. The pin effectiveness of the rectangular plate pin is often calculated by using properties of corresponding annular pin equivalent. So for which a graph of effective pin effectiveness is available as in figure 25. The corresponding annular pin has the same area in thickness as the plate pin it represents. Sabihin, yung rectangular mo, like, kunin mo yung area, tapos equate mo sa area ng annular pin. So, makukuha mo yung diameter niya. Yun ang gagamitin mo dito. External radius of the pin is RE. So, ito yung hanapin equivalent. Diba? Example number 8. Compute the pin effectiveness of an aluminum rectangular plate pin of a pinned air cooling evaporator. If the pins are 0.18 mm thick and mounted on a 16 mm OD tubes, the tube spacing is 40 mm in the direction of airflow and 45 mm vertically. The air side coefficient is 55 watts per meter squared Kelvin. Given, so 0.18 mm thick, 16 mm OD tubes. Tube spacing is 40 mm in the direction of airflow, 45 mm vertically. Air side coefficient 55 watts per meter squared Kelvin. This is now equal to S of F. Required pen effectiveness. Solution S of F 55 watts per meter squared Kelvin. Aluminum K 202 watt per meter Kelvin. Saan nakita? Walang 202 dito. So, hanapin mo dun sa book o sa table. 2y is 0.0018 mm. Y is 0.00009 mm. Ito. Divide mo ng 1,000. So, hindi ito mm. Mamaya. So, m is equal to the square root of h of f over k. Y is equal to the square root of 55 over 202. Divided by 0.00009 is square root is 55 per meter. So, pi equivalent external radius is pi times r sub b squared minus 16 over 2 squared is equal to 40 times 45 minus pi times 16 over 2 squared. This is the area of the plate, rectangular plate. Less mo yung area ng outside area ng tube. Okay? O D. Yan. So, this is now r sub b is equal to 23.94 mm. Or 0.02394 meter. R sub I is 8 mm or 0.008 meter. Then R sub E minus R sub I times M is equal to 0.02394 minus 0.008 times 55 is equal to 0.088. Well, yan. Wait na. Yan na. R sub E minus R sub I times the square root of S sub F over P sub I. Tapos hanapin. Yeah, wait lang. Ito, 0.88. R sub B over R sub I is 23.94 mm divided by 8 mm is 3. So from figure 25, hanapin mo yung this is M, di ba? So this is 0.88. This 3.88, andito siya. So guhit-guhitan nyo siya ng 10 division, tapos magiging 0.98, tapos hanapin mo yung ratio na 3. So ito. So hanapin mo yung katapat niya dyan, tapos ito yata. 0.60. Yan. So, gano'n. So, gawin ka ng line, tapos pagdating sa speed, gawin ka doon. So, this is now your value. 0.68. Answer. Okay? So, the air side area of a pin condenser or evaporator is composed of two portions. The prime area and the extended area. The prime area SOP is that part of the tube between the pins, and the extended area is of is that part is that of the pin. Kasi sa pins, meron pang space dun sa base, di ba? Since the prime area is at the base temperature, it has a pin effectiveness of 1.0. It is to the extended surface that the pin effectiveness less than 1.0 apply. So equation for the overall heat transfer coefficient can be revised to read, if hindi siya negligible, as 1 over U sub O A sub O is equal to 1 over U sub by A sub I is equal to 1 over H sub F times A sub T plus pin effectiveness times A sub A plus X over K A sub F plus 1 over A sub I A sub I. So, mabusis ito. Kaya kailangan mo yung pin spacing. Pin spacing, so makikita mo doon yung sa thickness, yung sa tubo, makikita mo yung spacing niya hindi center to center, kundi wall to wall sa pins, doon mo makukuha yung prime area. Okay? So, mahaba to sa heat transfer. This is for the liquid. Ay, air to. This is theory of pins. So for the gas flowing over pin tube, heat transfer and pressure drop. A precise prediction of the air side heat transfer coefficient when the air flows over pin tube is complicated because the values is a function of geometric factors, that is the pin spacing, the diameter of the tube, and the number of rows tube depths. Usually, the coefficient varies approximately at the square root of the phase velocity of the air. This one, air to eh. Air to, ito yung water cycle o refrigerant. Dito naman tayo, dito, pagkuhan yan. So, a rough estimate of air side coefficient HMF can be computed from the equation derived from illustrative data in the RA standard. HMF is equal to 38 times B exponent 0.5, where B is the phase velocity in meter per second. So, may unit itong velocity. Ang labos naman yan is watt per meter per cube. So, pag SI, so, convert na muna bago magamit yan. Now, next, the drop in pressure of the air flowing through a pin coil is also dependent upon the geometry of the coil. So figure 26 shows the pressure drop of commercial cooling coil when the pin surface are dry. So pressure drop of air flowing to a pin coil. Yan. Ito, phase velocity. Start mo na yung pilang pins per inch o pins per meter. Makuha mo yung pressure drop. Sa pins. Okay? So, sa mga brochure, sa carrier, mga aircon, may mga table sila ng pressure drop. Next, required condensing capacity. So, meron tayong tinatawag na heat rejection ratio. The required rate of heat transfer in the condenser is predominantly a function of the refrigerating capacity and the temperature of evaporation and condensation. Kapartner niya. The condenser must reject both the energy absorbed by the evaporator and the heat of compression added by the compressor. I-add mo yun ang size ng condenser mo. That's a term often used to relate the rate of heat flow at the condenser, so that of evaporator is the heat rejection ratio. Heat rejection ratio is rate of heat rejected at condenser in kilowatt divided by the rate of heat rejected at evaporator in kilowatts. So ito yung graph, typical values of heat rejection ratio as shown in figure 57. So typical values of the ratio of heat rejected at condenser to the refrigerating capacity for refrigerants 12 and 22. So yan. Sa application nito, pag nag-apply kayo, pag nagtrabaho na kayo, malaman nyo na yung application niya. Table ito, magamit nyo ito, this pag-design. Okay? Condensing coefficient. Sa refrigerant mo, nag-condense yun, di ba? Pagdating sa condenser. Nag-evaporate naman pagdating sa evaporator. So, dito tayo sa condensing coefficient. So, the basic equation for calculating the local coefficient of heat transfer of vapor condensing on a vertical plate, figure 28, was developed by Nosser by pure physical analysis. So, the equation for local condensing coefficient is H sub CB times X over K is equal to, enclose mo sa parentheses, G times rho squared H sub FG times X cubed over 4 over mu times over K over delta T exponent 1/4. Where H sub CB is the local condensing coefficient on vertical plate and watts per meter squared Kelvin. X is the vertical distance measured from the top of the plate. G is the acceleration due to gravity. Rho, density of condensate. S sub Ft, latent heat of vaporization. Mu is the viscosity of condensate. And the T, temperature difference between vapor and the plate. Yan. So, transfer ulit nyo to, tinuskas na doon. Condensation, meron pa ka doon boiling. So, iba mo ang boiling, di ba? So, hanapin nyo doon sa mga solutions. Solve problem ko rin to. So, the main condensing coefficient over the total height of the plate L is equal to bar h sub CB is equal to the integral of h sub CB dx from 0 to L divided by L is 0.943 times d rho squared h sub ftk cube over mu delta T L 0.14 and watts per meter squared Kelvin. Okay. So, the equation for the mean condensing coefficient for vapor condensing in on outside of horizontal tube is h sub ct is equal to 0.725 times g rho squared s of fg k cube over mu delta t and d 0.14 watts per meter squared Kelvin, where n is the number of tubes in vertical law, d is the OD of the tube. Okay? So, unit niya, di siya makancel. Okay. So, check nyo lang yung units. This is yata dimensionless. This is a dimensionless. So, any units yan. Dimensionless to. Example number 9. Calculate the main condensing heat transfer coefficient when refrigerant 12 condenses on the outside of horizontal tube in a shell-in-tube condenser. The outside diameter of the tube is 19 mm and the vertical loss of tubes there are respectively 2, 3, 4, 3, and 2 tubes. Refrigerant is condensing at a temperature of 52C and the temperature of the tube is 44C. Given refrigerant 12, OD 19 mm, vertical loss of tube is 2, 3, 4, 3, 2. Condensing temperature 52C, temperature of tubes 44C. Required is the main condensing heat transfer coefficient. Solution: the condensing coefficient is H con is 0.725 times E rho squared H sub F T K cube over mu delta T and D 0.14. So table A-5 at 52C. So H sub F is equal to 370.997 minus 251.004 or 119.993 kJ per kilogram. So this is the H sub Ft. And rho is equal to 1 over 0.83179 liter per kilogram or 1 to 02 kilogram per cubic meter. So table, di kasi doon. 15-5, liquid refrigerant 12, refrigeration and conditioning stock engines. Ito pa yung properties na makukuha mo yung dalawa. Yung nag-capital. So, sa table 15-5, mu is equal to 0.00017 Pascal second. Tingnan yung Stoker and Jones. Sa loob ng text, sa libro man on the table 15-5, andun yung properties. K is equal to 0.05932 watt per meter Kelvin. N is the average. N2 plus 3 plus 4 plus 3 plus 2 divided by 5 is 2.8. Delta T is 52 minus 44 or 8K. Since pwede siyang 8C or 8K. G is 9.81 meter per second squared. Ang ginagamit na natin. D is 19 mm or 0.019 meters. Therefore, substitute values. H con is 0.725 times 9.81 times 1202 squared times 119,993 times 0.05931 cube over 0.000174 divided by 8 divided by 2.8 divided by 0.019 0.14. So H con is 1065 watts per meter squared Kelvin. This is now the answer.